Here you go, Chad. Recording. Everything's recording. Ready. Okay, I got some kind of confirmation that exists. All right, let's get started. Haribo 836. I got a brainwave and hence a question concerning the lunar hopper drones. What minimum altitude would a stable lunar orbit be? With an atmosphere, could you orbit a reconnaissance drone at 1 kilometer or even lower around the moon? So there is no atmosphere at the moon, and this is something that brings regular satellites around the Earth back down. It causes them to re-enter the Earth's atmosphere, and the rate at that their orbits decay depends on their altitude. And so if a satellite is, say, 500 kilometers altitude, sort of at the height of the International Space Station or the height of the Starlink satellites, then they've got about a year and a half. They need some kind of station keeping to stay at that altitude. You go higher and you're running into less atmosphere, you're going to take longer, and then it could take a decade, and then eventually you could take a century, and then a millennia, and then effectively forever if you're far enough away. So your geostationary orbit, you're not going to be re-entering the Earth's atmosphere because of atmospheric drag. It's going to be through gravitational interactions with various objects in the solar system. The moon, as you stated, has no atmosphere. And so you're not dealing with sort of friction from the atmospheric drag. There is an atmosphere. I mean, it's not nothing. It's like 10 to the -6 bars of pressure. So it is like 1/millionth the pressure of the Earth's atmosphere. And they call it an exosphere. It's just like a collection of particles that are trapped around the moon briefly, and they don't build up. And so there is no real appreciable atmosphere. But the moon has a very lumpy, bumpy gravitational field. And so when you think about, it's very mountainous. There are mountains that can be thousands of meters high, and your spacecraft is going in orbit around the moon, and it is rising and falling depending on the shape of all of these gravitational field interactions. And so below a certain point, around 50 kilometers altitude, your orbit is going to decay just through the interactions with the gravitational field. But there are some sort of balance points that astronomers have worked up by mapping the gravitational field of the moon. And so if you can put your spacecraft into these stable orbits, and then you can bring the altitude down to whatever's the minimum, like around 50-ish, then you can remain in orbit for a very long time. You absolutely cannot orbit at 1 kilometer altitude. You're going to crash into a mountain. But even if you tried to orbit at 1 kilometer above the tallest mountain on the moon that you would potentially be flying over, you're still going to eventually crash into the moon because of this lumpy, bumpy gravitational field of the moon. And in fact, spacecraft have been sent to the moon, and like the Grail mission, and they haven't lasted as long as people had hoped because of this sort of decaying orbit due to the gravitational field. So, even without an atmosphere, spacecraft will still have their orbits decay. All right. Hey, everyone. Welcome back to the weekly question show. I apologize last week. I felt fine, but I just sounded gross. And you can still hear it a little bit in my voice. Something in Japan nestled into my sinus and lungs and decided to just stay there. And so I was coughing and sniffing and hemming, and I'm going to be doing that again in this episode, but it is so much better than it was last week. Like last week I got set up, I was ready to live stream, and I just said, I can't do this. Like, this is just going to be great. Like, people are going to be grossed out listening to my phlegmatic voice and annoyed by my constant coughing. We could edit it out so the final thing would work, but instead I just hung out with my wife, watched Rick and Morty, and fell asleep early. So yeah, but I do apologize for all of the dad noises that I'm going to be making in this episode. I will be making them. I'm gonna have to clear my throat right now. I can hear it. So, yeah, but apart from that, I feel great. So for those of you who are wondering what it is that you have stumbled into, this is going to be a live episode of my weekly question show. So I will be sticking around for 2 hours on this lovely Monday evening, and I will answer your questions about space and astronomy. So go ahead and put any questions that you might have into the... I'll answer that question. Put any questions that you might have into the chat here on YouTube, and then that will be slurped into a database that I am using to operate this show, and then I will be able to answer your questions in rapid fire as quickly as I can. No distractions, no looking around at the chat. Man, like, side note, here comes a rant. I find most live streams intolerable because of that kind of, hey guys, how's it going? Oh, what's happening over there? Oh yeah, it's squirrel. But no, I am focused. I have to answer the questions one after the other. We get this done. So, but ground rules. If this is, I know how many times I have answered your questions. And so if you've never had a question answered before, you show up. It highlights. I know that you've never had a question answered before, and I can't wait to answer your question. Now I'm going to sneeze. Oh, maybe I'm not ready. Okay. Second, which is just remember that I am a journalist, not a scientist. And so if you want my nuanced opinion about some scientific matter, I cannot provide you one. I can only sort of give you the scientific consensus. And again, don't make me begin a rant about why trusting the scientific consensus is the right move, because I will drop that rant at a heartbeat. And then the third thing is, of course, we get a ton of questions. I really try to avoid repetition. I'm going to answer your question if I don't know the answer. And so it's not like there's nothing personal. Your question is there. I see it in the database, and for some reason I am not answering it, but I will only get to a fraction of the questions that we get during this episode. So don't worry, but don't ask your question a bunch of times. It's there. I got it. We saw it. So that's what's nice about the, having this database, is that your question stays with me forever in my heart. Okay, let's get going. 1001. Fraser, do you ever end up using all your patience on us in the QA and then be short with your family? No, absolutely not. It's funny. When I'm about to do the question show, when I'm about to sit down and do a 2-hour live stream, I definitely feel a certain amount of, not nervousness, but kind of resistance, just because I have to go and sit in, do this thing for 2 hours. Like it's a very high energy activity. Now, anybody who knows me personally, my family, my friends, my children, we're colleagues, people who know me. Like, I am exactly the same. Like, what you're seeing here is identical to what I am in the day, but I don't like sit for 2 hours and just focused energy and answer all of these questions about space. I'm usually wanting to talk about gardening. So, it requires a lot of energy. And so after it, I'm just kind of worn out. I'm just beat up. Like, my brain is mush. And so I just sort of fall into bed and watch TV like a vegetable with my wife. That is, so no, absolutely not. No, it's funny. Like, I think, man, oh no, you know what? If I tell you this, all right, well, I will. Which is, I find, like I think a lot of people get really exhausted and annoyed by what is considered to be stupid questions or repeat questions or stuff like that. And it doesn't bother me one bit. Like, as long as a person is asking a question from a genuine place of wanting to know the answer, like if they are honestly asking this question because they don't know the answer, then I don't care how little they know about the topic, right? Like, this is a chance to educate. This is a chance to bring a person one step closer to the beauty and the wonder that is the scientific method and our search for understanding in the cosmos, like all of this stuff. And I am the on-ramp, and I am so honored to be able to do that. And so I find that really fun. And I even kind of find it fun when people are assholes. Kind of. And not like just like straight up obvious trolls. Like, if people are just total trolls, well then, you know, who cares? Like, they're awful. They can just go away and I don't want to hear from them. You know, like, this is no fun for me. If only one person is having fun, then that's called bullying, right? So trolls can suck it. But people who are sort of conspiracy minded or are sort of flabbergasted that we believe in all of this space stuff, I find that very fascinating because those people love space. Like, obviously, like, why would you like for the things that I don't like, mushrooms. I don't go onto discussion forums where people are talking about mushrooms and tell them how much I hate mushrooms, right? I just don't like them. I don't want to eat them. I don't want to eat mushrooms. And like, I know some of you freaking out. I'm sorry. I apologize. I'm not a mushroom fan. The raw's okay, but cooked, oh, it's so slimy. Anyway, so what does it take? What is the mindset of a person who is so angry or so furious about this topic of space, about people walking on the moon or people exploring the solar system or us observing the cosmos, that they go to places where people are enthusiastically talking about the thing that they don't want to talk about and they don't want to hear about and they don't believe is real, and then they want to engage, they want to proselytize, they want to market their ideas. I think at the heart of it is a person who once loved space, once believed in the moon landings and all this, you know, in astronomy and all this kind of stuff. And then they went down some kind of conspiracy rabbit hole, and now they've come out the other side, and now they're on a sort of crusade to punish those who are bringing about the great lie. But at their heart, they are that 5-year-old that watched space television shows in wonder. And that person is still in there. And I feel like I can fix them. I can bring them back. I can connect because, like, literally we both agree that space is awesome. And I believe that it's real. And you believe that at some point someone convinced you that all the things that you loved aren't real. And boy, when you find out that those things are real, you're going to be so mad, right? And I want to be there for it because that will sort of bring you back to the fold. And you know, I think that because, like, why would you stick around in communities that you don't want to be part of? No, you want to be part of this. You want to convince us that the thing that you love and we love isn't true. And boy, we've all been taken advantage of. And I want to convince you that this thing that you love and I love, it's real and it's okay. Come on back. Come on back. So, yeah. It's like, just to be clear, I know that I am in the wrong for not liking mushrooms. Like, this is, man, I've got a worse one. All right. I don't like avocados. I just don't like them. And I want to like them. And I have tried my level best to like avocados. I have sat and eaten entire avocados going, this is supposed to be a delicious food and I am supposed to enjoy it. And it's just this kind of mushy, ugh, I don't like it. I don't like it. And I know it's healthy. It's good fats. It's fresh from the tree. You can grow them in tropical environments. I was in Hawaii and I was picking avocados off the ground. But I can't eat them. Okay. Jake Gajoff. What are the main causes for making an orbiting object in a solar system tidally locked versus spinning? So tidal locking is this inevitable event that happens given long enough time and if two objects are close enough together and something is irregular. So what happens is, and we'll sort of use the example of the Earth and the moon. So the moon is in orbit around the Earth and the Earth is pulling at the moon is pulling at the Earth, and the Earth is sort of pulling a different amount on the moon on its front versus the back, because the back of the moon is farther away from the Earth than the front of the moon is. And so this causes a sort of an elongation of the moon. It kind of turns it into, from what would be a sphere, although it's, into something that's like a little bit of a flattened sphere. And so let's say the moon is rotating, and used to be the moon was much closer to the Earth than it is today. And so the moon was rotating, but it was being pulled differentially on these, what I like to call handles. And so you get this torque effect on the moon from the gravity of the Earth. And so the moon would just be slowing down and slowing down and slowing down. And eventually the orbit of the moon would just stop. It would be tidally locked to the Earth. And this is the same effect that happened to all of the Jovian moons. It's what, when you hear about all of these exoplanets that are tidally locked to their stars, it's the same process. And in fact, the moon is causing the Earth to try to be tidally locked to the moon. So the moon's gravity is pulling on the Earth. It's causing a bulge, a tidal bulge on planet Earth. And these are handles that the moon grabs onto as the Earth is rotating sort of under its gravitational field. And it is slowly trying to slow down the rotation of the Earth. And because you need to have this conservation of angular momentum between the Earth and the moon, as the Earth's orbit is slowed down, we lose, I forget what it is, like a couple of milliseconds every century, the moon drifts farther away from the Earth to compensate. And in about 50 billion years, the moon will have slowed down the rotation of the Earth to the point that now the Earth and the moon are both tidally locked to each other. But of course, the sun will have been burnt out, and probably the sun will have consumed the Earth at that point. But you see that with Pluto and Charon. So you've got these two objects that are roughly the same-ish scale, and they're tidally locked to each other. So tidally locking is the natural effect. And so sort of an interesting flavor of this, it really all just depends on your altitude of the object that is orbiting around the moon above the larger object. And so the Earth takes 24 hours to turn once on its axis, while the moon takes 28 days to do one orbit around the Earth. And so because the orbital time of the moon is longer than the rotation time of the Earth slows down and the moon drifts away. But if the moon is orbiting so quickly that it is orbiting more rapidly than the orbit of the planet, then you get the inverse. So the moon speeds up the orbit of the planet and the moon draws in closer to compensate. And the example of this is Phobos, which is orbiting around Mars. So a day on Mars is a little over a day on Earth. It's like 24 and a half hours to orbit, but Phobos only takes about 8 hours to do one orbit around Mars. And so now this torque, this tidal effect caused by the interactions of the gravity of Phobos and the gravity of Mars works in reverse. Phobos is going around faster than Mars is, and so it's grabbing onto those handles, and it is pulling Mars to orbit more quickly and more quickly and more quickly. And to compensate, the orbit of Phobos is degrading. And eventually, in about 50 to 100 million years from now, Phobos will cross the Roche limit, get torn apart, and then rain down on the surface of Mars. So yeah, any two objects orbiting around each other that, if there's any kind of way for them to be torqued, they will tidally lock with each other. Silo 87. Is the cost to send a repair update mission for Hubble greater than a new Hubble-sized telescope, considering the military discount mirrors that NASA got? Right, so there's a whole bunch of questions that you're kind of mashing here together. So the first thing is, what would it cost to repair the Hubble Space Telescope? And, back in the day, there was the space shuttle, and the space shuttle flew, and it was able to do servicing missions for the Hubble Space Telescope. And I don't know the price of the servicing missions. They were in the couple of $1 billion range, which is what the space shuttle cost to be able to do flights, 500 million to a couple of billion, depending on what the cargo was and what the mission was doing. So let's say that it's $1 billion to service the Hubble Space Telescope. That means to fly a space shuttle, dock with the Hubble Space Telescope, upgrade the instruments on board, replace any of the gyros, any of the parts that could be reaching the end of life, and then give it a boost to raise its altitude again so that it has many more years to go. That's a lot of money, but it is definitely less money than it cost to build the Hubble Space Telescope in the first place, and that's why they were doing the servicing missions. But now we don't have the space shuttle. Space shuttle doesn't exist. And now we don't have a spacecraft that is capable of doing servicing in the way that the space shuttle did. It had the robotic arm, the Canadarm, that was able to grab onto the Hubble Space Telescope, bring it to the bay of the space shuttle. They were able to go out from the shuttle and be able to perform the docking operations. And then it was able to release it again on the higher altitude. But a couple of years ago, Jared Isaacman, actually, who's the new NASA administrator, pitched to NASA that they would like to do a sort of a private partnership mission to repair the Hubble Space Telescope or service it. And they would use a SpaceX Crew Dragon, which is the same spacecraft that's used to deliver astronauts to the International Space Station, and that they would perform that operation on Hubble. And that it would, and I forget the budget, but it was like in the 500 million-ish range. And NASA said, thank you very much, but this is freaking us out because that you're not having a spacecraft that really has the docking bay that's really designed for this kind of operation. You've got people docking on a Crew Dragon, doing spacewalks, trying to perform these repairs, where they're going to keep the spare parts. And the concern was, what if it accidentally bumps, causes any damage to the Hubble Space Telescope? And then this would be a big problem, because now you wouldn't get the remaining years of Hubble, you would have less years. And building a new Hubble telescope would be very expensive. And as you said, NASA got the 2 donated Hubble class mirrors from the National Reconnaissance Office. One is in Nancy Grace Roman, and it's launching in 2 months. So don't use that one, but they still have the other one. And so could they theoretically build another Hubble Space Telescope around that other mirror? Yeah, they could, but they don't have the budget for that. That all of the future budget is going to different scientific priorities down the road. So you've got the main big flagship mission is going to be the Habitable Worlds Observatory. And that is going to be a James Webb class. So a 6.5 meter mirror, which is much bigger than the 2.4 meter mirror that was in the Hubble Space Telescope. So it all comes down to a lack of funding. That if NASA had unlimited funding, then I'm sure somebody would replacement Hubble. It would be a few $1 billion. Let's say $4 billion to build another Hubble. Or you spend $1 billion to repair Hubble and sort of see if that gives you more life on it. But really, NASA doesn't have either of that funding. They have the funding potentially, maybe someday, to build the Habitable Worlds Observatory. They have very limited options. The Mars sample return mission was canceled. The administration recently tried to cancel dozens of missions. So this is not the time that NASA's like, I wonder if we could just like build another Hubble. That'd be cool, right? They just don't have the budget for it. That said, the Chinese Space Agency is building their version of the Hubble Space Telescope, which is going to be, it's going to be around the same size as the Hubble Space Telescope. And is it Tiantian? Anyway, they're going to be in sort of flying it in formation with the Chinese space station. And so when they need to service this telescope, they'll have it maneuver in, dock with the station. They'll be able to spacewalk out of the station, do their repairs, and then send it off. And so it's going to be roughly the same size as the Hubble Space Telescope, but it's going to have all of the modern instruments of 2026 as opposed to instruments of 1990 that have been repaired and upgraded since then. William Hallman, Fraser, what are your thoughts on Elon Musk becoming the first trillionaire? I mean, I don't care. Yeah, so SpaceX is a public company, which makes sense. I mean, they are, they have a lot of capital demands. They're launching rockets. They're launching communication networks. They've gone all in on AI, and so they're going to need to be able to fund their operations. And so they've done this IPO and gone public and raised something like $75-80 billion, and started out at a share price of like 135, and then went up to, I think at the time that I'm recording, they're up around 185. So that's a quite impressive growth. And for the people who got on board early on, you've close to doubled your money. It's a lot. It's a big valuation, though. I mean, it is a almost $2 trillion valuation at this point. One of the largest, most valued companies in the world, and there's a lot of risk. They're losing a lot of money on the rocket side. They're losing a lot of money on the AI side. They're making money on the Starlink side, on the telecommunication side. But the question is, will they be able to just keep this going for the years and decades that it takes? They're putting all of their bet on data centers in space, which is sort of betting that the AI boom is going to continue, and then it's going to turn into data centers in space, and that engineering makes sense. Many people are skeptical about that. I've seen suggestions that it's not as a crazy idea as it seems. I remain to be convinced. So yeah, I don't really have a lot of thoughts about it. I mean, I think SpaceX has obligations to deliver the human landing system for the upcoming Artemis 4 mission, and demonstrate the capability of their lander for the Artemis 3 mission, which is next year. And the development of the version 3 of Starship has taken a while, and so they are right there on the critical path to be able to make this mission happen. So if going public gives them the funding to be able to make sure that they can hit those milestones and deliver their part of this mission, then that would be good. And yeah, I mean, I think that there's like a lot of emotions that are tied up in this public offering, and just like the billionaire class in general, because you have, on the one hand, all of this support for a lot of really bad policies. A lot of damage has been done to global health efforts, with the cutting, all of the cuts that were made to USAID and all of the stuff in the US government. And, there have been increases of screwworms in the United States, and there is an Ebola outbreak. There are some really important things that these international aid agencies are doing, and a lot of the cuts were led by Elon Musk. And so I think like a lot of people are really angry about him personally and sort of his role and involvement in some of the stuff that's happened recently. And then on the other hand, SpaceX makes rockets that land on drones in the ocean, and then they can reuse them for dozens of times. It's kind of amazing. And it's not just the leader. There are thousands and thousands of engineers that are working on this, that are attempting to bring this next capability of spaceflight. And, we talked about sort of the pollution caused by rockets crashing into the ocean. This whole situation of rockets crashing into the ocean is the result because nobody has developed reusable rockets. That, we don't crash airplanes into the ocean after every launch. We don't light our cars on fire after every time we go to the grocery store. These things are reused. That really the technologies should be reused. And it's because rockets are right at the very limit, the very edge of what is possible, that up until this point, no company and organization has been able to make these things fully reusable. And that is the goal. That is the dream. SpaceX has demonstrated they can do it with the first stage, but they are still, it remains to be seen if they can do it with the upper stage. If they can, then you have a fully reusable rocket stack, a super heavy lift vehicle, and you will see the last time that a rocket needs to be intentionally destroyed. There are hundreds of rockets that are crashed into the ocean, or in China they crash them into downrange on the land, sometimes villages. Like, it's an enormous waste and damage to the environment. And then all of those upper stages re-enter the Earth's atmosphere and burn up and contribute to ozone depletion. And there's all kinds of downstream problems. And we would have the same kinds of problems if every time someone flew an airplane, they crashed that airplane into, the runway when they were done with it. I don't know. And so, man, if we could get to this place where we no longer destroy rocket ships, and whether it's SpaceX that does it, or whether it's Blue Origin that does it, another billionaire, or whether it's the Chinese that do it. Like, the Chinese are working on, they have many companies that are working on what appear to be total clones of the things that SpaceX and New Origin, that Blue Origin are doing. I really want someone to crack this, because reusable rockets are better than disposable rockets. Think about the Space Launch System. When the Space Launch System launches, you're taking this enormous foam-covered liquid hydrogen, liquid oxygen fuel tank with engines on the bottom, and you're crashing into the ocean. You've got these two solid rocket boosters that have a lot of harmful chemicals in them that are dumped into the ocean. And the time for us to crash rockets into the ocean is over. And the time for us using fully reusable rockets has begun. And so I don't, if SpaceX can pull it off, then their valuation is probably justified, and they probably are one of the most valuable companies that has ever been created. And if they are just unable to pull this off, and they struggle with it for decades, and they eventually run out of cash and their share price goes down, well, then hopefully somebody else figures it out. So I am sort of just waiting to see what the final balance of this whole thing is going to be down the road. And I think the thing that is sort of weird to me is sort of the structure of the company, the voting rights that Musk has compared to the voting rights of the other people. It seems like a bad deal for regular shareholders who essentially have no control over the company. And so I think, if I was a shareholder in the company, I would want to be able to have more say over what the future of the company has. So, yeah. So right now, I think it's too soon to tell. And it doesn't really make any meaningful change to the company. The company still is launching rockets. They are providing internet service. They are sending humans to and from the International Space Station. They are working on their next generation fully reusable two-stage rocket. They are providing the landing system for NASA. They are selling AI compute in these gigantic data clusters to Google and Anthropic and other companies. And who knows what's going to happen. And so now it's like this company already existed. Now it's a public company. Where is it here? Ventura, Fraser, why didn't Canada step up and donate billions to trans the tribes in Africa when Elon took the funds away? It must be nice to demand a foreign nation spend money how you see fit. Hey, Canada does its part for the international community at the rate that we can, and the United States was seen as sort of one of the good guys, like one of the nations that saw the health of humanity as a thing that was very important, not just for doing the right thing, not for providing a good to humanity, but also understanding that having less disease, less screwworm infections was sort of good for the long-term health of their nation as well. So obviously, I'm a Canadian. I can sort of watch from afar and have opinions about what the United States does. Like that's fine. And I also have opinions about what my own country does. Also fine. And you're free to have opinions about what my country does. Feel free. And when it comes down to it, you vote for your country, I'll vote for my country, and we will sort of watch how it all plays out over the long term. But if you think that making friends with people around the world is important, if you think that sort of having good, firm allies is important, then there are certain behaviors that you would take. And if you don't, then there are other behaviors that you would take. Okay. Aaron929. Fraser, is there best direction to look for meteors if one is quickly looking at the sky? Planet ecliptic, forward direction of the Earth's travel. So it depends on the meteor shower that you are attempting to see. So in fact, the meteor showers are named after the constellation where they appear to originate. So the Perseids meteor shower appears to originate from the constellation Perseus. The Geminid meteor shower appears to originate from the constellation Gemini. The Leonids appear to originate from the constellation Leo. And you can see this, like if you know where your constellations are, then you can go out at night and you can sort of watch that constellation and you will see the meteors are coming out like a star coming out from that central region. But you don't have to be watching that region to see the meteors. They'll happen anywhere in the sky. It's just that if you sort of trace the line back, you would end up at where that spot was. And so I was going to say, oh yeah. So, but there is a general background level of meteors that are happening all night, every night. And so if you just like go out any single night, any time of the year, look up, and wait for about a minute or two, you will see a meteor. And that is the background level. And so generally when astronomers calculate the meteors per hour that you could see from any one meteor shower, they're sort of like, what is the additional meters that you see above and beyond the background? And those can come from any direction. It's interesting, sort of early on in the night, like just after sunset, you get a specific class of meteors called, what are they called? Sky grazers? So you get these sort of much longer meteors that will like leave a very long trail, and they're really cool. So often it's good to start looking for meteors even like shortly after sunset. And then sort of right in the middle of the night, you can get ones that come in almost directly. And so you don't get the big long streak. You almost get this sort of explosion in the sky because you're looking face on to the meteor that is coming in. So, but yeah, you can see a meteor any night. You don't like, if you want to see a meteor, find dark skies, watch the sky for a while with some friends, hang out, and you'll see meteors. The film, how hot black holes are. So the question I think you're asking is how hot are black holes? And there's sort of like two answers to this question. So the first answer is the environment around the black hole. So not the black hole itself. So, black hole is obviously this mass that has been compressed down to some ridiculous amount. It's surrounded by this event horizon, and the black hole is spinning. All black holes seem to be spinning, and they're often spinning sort of at the maximum rate that they can, sort of like 65% the speed of light as they're rotating. And they're surrounded by this sort of twisted space-time, very powerful magnetic fields. Magnetic fields are interacting with the material that is trying to fall into the black hole, the accretion disk around it, and that gets compressed and heats up to millions of degrees. So you've got this environment around the black hole where stuff is heating up. It's kind of like the interior of a star. It's shining with X-ray radiation that you can see with space telescopes. It's as if you were looking into the center of a star. And in fact, around the biggest black holes, they're actually creating new elements in the accretion disks around them because of this star-like environment that is around the black hole. But that is not coming from the black hole. And people say, like, why can there be radiation coming from a black hole when nothing can leave the black hole? Well, it's not coming from the black hole. It's coming from the environment around the black hole. The black hole spinning, interacting with its environment. You get these jets and winds that come out. And if you're staring right down the barrel of one of these jets, that is a quasar that you're seeing, or not exactly. That's a blazar. And then if you're seeing it a little off to the side, then that's a quasar. And you are seeing this super bright jet of material that is coming out of the star. Sort of a classic example. If you look at M87, which is one of the supermassive black holes that was seen by the Event Horizon Telescope, you can see this jet of material that is coming out of the black hole. It's amazing. So that is the temperature of the environment around the black hole, but that's not the temperature of the black hole itself. Black holes absorb everything that falls into them, all of the matter, all of the energy, and nothing, not even light, can escape the black hole. Not even radiation. Radiation is just light. It tries to move at the speed of light. You have to go, even moving at the speed of light, you cannot escape the grasp of a black hole. And yet, black holes have temperature. And this is sort of this incredible realization made by Stephen Hawking, like back in the 1970s, I think, that he figured out on sort of the way black holes work and the way they interact with their environment, that you would actually, an outside observer would measure radiation coming off of a black hole that radiation has to come from the mass of the black hole, that there's no other way that you can get that radiation. It has to come from the black hole. And so in order to be able to give off radiation, to give off heat, the black hole has to evaporate. And the temperature of the black hole depends on the mass of the black hole. When the black hole starts out, say it's something that is a billion times the mass of the sun, like a supermassive black hole, then it's going to have a temperature that's just like tiny little bit above absolute zero. But as the black hole runs out of, as it evaporates, it gets hotter and hotter and hotter. And eventually, when the black hole has like the mass of a mountain, it is glowing in X-rays, super bright, and then eventually it just sort of explodes in this puff of gamma radiation because it's just gotten so hot. But the evaporation of black holes depends on the ambient temperature of the universe itself. Like right now, the ambient temperature of the universe is 2.7 Kelvin, so 2.7 degrees above absolute zero. And so right now, all of the biggest black holes are absorbing radiation from the background temperature of the universe. But over time, as that background temperature cools down, eventually it will go below the ambient temperature of the black hole, depending on its mass. And then the black holes will start to evaporate and eventually fade away after a googly years. William Hallman, it seems like you know as much as a regular scientist. Why did you not just become a regular scientist or an astrophysicist? I don't know as much as a regular scientist. I'm a journalist. So I know a very specific, kind of information. My knowledge is very broad, but it is not very deep. So if you wanted me to do the math, which is the language that astronomers and physicists speak, I would not be able to do the math. And that I have to rely on them as scientists to be able to give me the information that is accurate. So, so like, why didn't I become a scientist? Well, so when I was in high school, I took lots of math. I took physics, chemistry, computer science. I also took journalism, which was kind of cool. And then I applied for the engineering, a bunch of engineering programs at various universities in Canada. My original dream was to be an aerospace engineer. And so I had applied for the engineering program at the University of British Columbia. And then my plan was to get my master's degree. There's a Canadian university that does aerospace engineering, and then try and get a job at NASA. And so I went to, and I was accepted into the engineering program at the University of British Columbia, class of 89, or I guess the entrance 89, and just hated it. I just didn't like it at all. It was just not my bag. And I was starting to realize that, most engineers ended up, mechanical engineers, which was the kind of engineer that I wanted to be, ended up working on heat ducts and heating and cooling systems for commercial buildings. And that just didn't seem interesting to me at all. And so I switched gears and went into computer science and really enjoyed that. And then went into working, sort of leading software teams, and then was doing journalism, space journalism on the side. And then after like a year of that, I'm like, oh wow, this is what I love. This is what I enjoy more than anything. So no, I think like some scientists are incredible communicators, but all scientists are busy doing science. Like that's their primary job, is to do the science, but they need help communicating both the discoveries that they're making and the underlying methodologies that they depend on. That when you have conversations with people in conversations in discussion forums who like have a profound misunderstanding about how science works, right? You hear people talk about dark energy or dark matter in this sort of eye-rolling way. Well, scientists just, they just make up fudge. It's this conspiracy, this agreement. Like that is not how science works. Science is this sort of brutal Thunderdome style skeptical inquiry where anyone who wants to propose an idea has to undergo a withering hail from all of the rest of the scientific community. And if their ideas can withstand the pressure, then people will provisionally accept it until they can defeat it later on. And so my job, like the need that I think is out there is to help scientists communicate both the work, the specific discoveries that they're making in a way that is relatable to an audience, and to like be a cheerleader for the scientific method, for the system, which I think is, for all of its flaws, it is the best system that has ever been developed for uncovering the true nature of reality. And we live in this modern society with all these incredible wonders around us. We owe all that to science, and science gets the job done. So no, I'm perfectly happy in the role that I'm in. I have, and sometimes I will like be having an interview with somebody and I will ask what I think is a very insightful question. And you can just tell they've heard this, they've thought of that. They've heard this question before. So, I have nothing directly useful to contribute to the scientific conversation. The best value that I can do is I can be a bridge builder between scientists. I'm like, oh yeah, did you hear that this person over here is working on this thing over there? And like, oh great. And that I can provide information to scientists that, while they're on their downtime, when they're eating their breakfast, they can watch our news or watch a question show or watch some of the interviews that I'm doing. They can find out about what their scientific colleagues are doing. But no, I have no interest in being an astrophysicist, no interest in being a scientist. I love my job, and it is a very specific and I think important job. And I wish there was more science communication that was done, because the kind of conversations that you see in the chat demonstrates sort of often a profound misunderstanding of how science works. And so like my hope is that by watching the content that we create, or the content that the question shows that I do, the way I approach these problems, you have gained a deeper understanding of the scientific method and a deeper understanding of what's happening in space and astronomy. Like if I've done that, if you could attribute some of your understanding, your knowledge of how science works, that I helped you with that, then man, that is the best. I can retire happy. Not that I'm going to retire, but when I do, I'll be happy because I helped. I did my part. Alaskan ballistics. Got any gardening advice for those of us in the northern climates? I'm assuming you're in Alaska, which is a brutal climate zone. So I don't really. I live on the west coast of Canada, so our gardening zone is pretty good, and so we can grow not quite tropical plants here, but we can grow pretty mild temperature type plants. I can grow pomegranates here. I can grow figs. I can grow lots of fruit, berries. So I'm very lucky with the part of Canada that I live in. I can't even imagine how hard it would be to grow stuff in Alaska. I don't know, plums, blueberries. Yeah, it's rough. DO6769. Astronomical measurements. What are the various units and how do they relate to each other? I know light year and all AU, and then there are some ladder stuff and redshift stuff thrown in. Thanks. There's like two parts to this, right? Like, what are the different methods that astronomers use to measure distance in the universe? And then what is the methodology that connects those measurements together? How do we know how far away things are in the universe? So I'll tackle them sort of one after the other. The first thing on the sort of methods of measurement, the astronomical unit. Obviously you can measure things in kilometers. You can measure things in hundreds of kilometers, millions of kilometers. The moon is 400,000 kilometers away. The Earth is 150 million kilometers away from the sun. Jupiter is 1 billion kilometers away from the sun. I forget all that. Jupiter is like 700 million kilometers away. I forget the exact numbers for some of these. And so an astronomical unit is the average distance from the Earth to the sun. It's like 149 million kilometers on average. And so instead of just measuring in hundreds of millions of kilometers, you can just say how many astronomical units is it. And so now you can measure things, 10 AU, 50 AU, 50 astronomical units. And so the solar system contains, or will go out to say, tens of thousands of astronomical units away, which is sort of where the outer limits of the Oort cloud are. So even, the entire distance from the Earth to the sun just becomes one of tens of thousands. And then of course light years. And it's the distance that light travels in 1 year. But you can have a light second. The moon is about a light second away from us. You can have a light minute. The sun is 8 light minutes away from us. It takes 8 minutes for light to travel from the sun to us. You can have light hours, light days, and of course light years. And a light year is 4 quadrillion kilometers. I apologize if I'm just sort of doing this off the top of my head. But like the nearest stars are like a little over 4 light years away from us. So it takes 4 years for light to travel from us to the nearest star system. And then the system of measurement that most astronomers use is the thing called the parsec. And the parsec is it's a very weird measurement, but the gist is that when you sort of define an angle to an object in the sky, and then you measure the angle to that thing when the Earth is on one side of the sun, and then 6 months later the Earth is on the other side of the sun, the thing that you're looking at will move back and forth in the sky. And this is the technique of astrometry. And you can essentially do trigonometry to find out the distance to that object. And sort of the classic example, of course, is you hold your thumb out at arm's length, and then you open up one eye at a time, and you watch as your thumb jumps back and forth. you could measure, you could calculate the distance your eyes are apart just by measuring how far away your thumb moves. Or you could calculate the distance to an object. You could calculate the distance to your thumb purely by measuring how far it jumps back and forth using trigonometry. So, all that math that you learned in high school is actually super useful. And so this measurement is called the parsec, and it's a little over 3 light years. And I forget the exact, it's like the amount that an object travels back and forth, based on the movement of the sun. And I forget all of the different pieces, but parsecs are done using that trigonometry, and it's a little over 3 light years away. And then astronomers will have kiloparsecs, so thousands of parsecs, and then they'll have megaparsecs and even gigaparsecs. And then the last measurement tool that astronomers use is called redshift. And you'll see like a Z equals something number. And that is essentially the speed that this object is moving away from us, because thanks to Hubble, we learned that the farther away something is, the faster it's moving away from us. And so astronomers will measure the redshift, and redshift 0 is about, it's a few billion light years away from us. Redshift, say 13, is stuff that is seen when the universe was around 300 million years old. Redshift 1000 is the cosmic microwave background radiation. And so astronomers will typically, once things get really far away, they'll just define them in terms of redshift. And you can calculate, you can convert redshift into tens of millions of light years or hundreds of millions of light years or billions of light years. The problem is that the distance doesn't make sense anymore, because you're moving, they're moving, and the universe has expanded in between in the billions of years that these things have existed. And so, often people will say, well, astronomers are looking at a galaxy seen when the universe was only 1 billion years old. And so that galaxy is 13 billion light years away. And not true. The galaxy is actually not 13 billion light years away. That galaxy is probably more like 20 or 30 billion light years away today, but the light has been traveling to us for 13 billion years. And so that's why astronomers switch to redshift, which is the sort of like one number that uses all of that. So that's like the distance tools that the astronomers use to sort of talk about distance in the universe. And then the second part of your question is like, what are the methods that they use to actually get there? And they have this overlapping system of measurements. And I spent more time on the explanations of the terms. I don't want to give it too much. I've gone into detail about the methods tons of times. I've interviewed Adam Rees, got a Nobel Prize because he's so good at this. But close up, astronomers use trigonometry to measure the distance to stars, and it is very, very accurate. You can measure this very carefully. And then the next level, they use a thing called Cepheid variable. So there's a type of star that changes in brightness on a variable period of time in a way that allows you to know the intrinsic brightness of the star. You look at how bright the star is, you know how far away it is. Then that gets you out to nearby galaxies. And then there's the type 1a supernova. This is the one that astronomers are able to use to learn about dark energy. And so type 1a supernova detonate with a very specific amount of energy. You calculate the brightness of the supernova. You know how bright it should have been. That allows you to calculate the distance. And then there are a bunch of other methods. They use the redshift. They can see how the light from a distant galaxy has shifted, and that allows them to essentially tell how far away that galaxy is, roughly. And then they can also use gravitational waves to determine the distance to objects. They can measure the light coming from quasars. There's like a whole range. There's about 20 parts to the distance ladder that overlap. And each piece of the distance ladder has been double-checked and checked against itself. And so astronomers have gotten very good. And then the final method is they're able to measure effectively the light in the cosmic microwave background radiation and use that to measure how fast that part of the universe is moving away from us, and therefore to calculate how old the universe is. Hope that helps. Philip, how do we stop the moon from getting farther away? We have to stop stop the rotation of the Earth compared to the moon. So if we could slow down the rotation of the Earth to the point that the Earth and the moon were tidally locked to each other, the moon is tidally locked to us, but if we were also tidally locked to the moon, then the moon would no longer be drifting away from us. Former Rosa Studio. Any new tech getting us closer to interstellar travel? Nope. The ideas for interstellar travel were suggested back in the 60s and sort of fleshed out in the 70s. Fusion power, light sails, antimatter rockets, and those same ideas are the best ideas that anyone has come up with today. Someone's asking if my mic is clipping. So let me know if the mic is clipping. I sort of accidentally changed the audio on the mic, and so I sort of reset it. And if I get like really loud, then it might clip a little bit. But typically people are complaining that my mic is too quiet. And I'm looking at the waveform and I can see it like clips a tiny little bit if I get really loud, which I do. Let's get on the bottom. Yakarin, you know, it would be funny if they discovered mushrooms or avocados on Mars. Yeah, that would be amazing. Would I eat them? After other people. Mist Solar. The Oort cloud visualization is almost always a perfect sphere. How does it keep its shape when interacting with other nearby gravitational objects and radiation while traveling? Yeah, so it's interesting when you see, you know, we have the plane of the ecliptic, or we have the way all of the planets are lined up around the sun. That, you know, obviously the sun formed from this nebula, the protostellar nebula. It spun up, flattened out, and then in the protostellar disk, the planets started to form. They gobbled up additional material, cleared out their orbits, and now everything is all lined up. But when you look at the illustrations of the Oort cloud, they're not lined up. They're more like this big sphere. And we know that the Oort cloud is a sphere because long period comets come from everywhere, come from all directions. They come randomly into the solar system, and they're not coming from along the plane of the ecliptic in the way that all of the other objects that we're familiar with, like the Kuiper Belt object, it's lined up around the solar equator, all the planets, all the centaurs, but no, the long period comets come in all directions. So why is that? Well, when you are in the Oort cloud, you are really far away from the sun, that your orbital velocity around the sun is very, very low. So Mercury is going at 48 kilometers per second around the sun. Earth is going 30 kilometers per second. Once you get out to Neptune, you're going 5 kilometers per second around the sun. And once you get out to the Oort cloud, you are going much slower. And that means that gravitational interactions between other Oort cloud objects can change your orbit. And so you have two Oort cloud objects that get relatively close to each other. They sort of tangle gravitationally, and then they go off in new directions. And so over time, over billions of years, that starts to make the Oort cloud more and more spherical over time. But there are some large-scale structures in the Oort cloud. So there was a paper that came out a couple of years ago, and we reported on that in Universe Today, that there are these sort of various donut shapes in the Oort cloud closer in to the solar system, and there's sort of structures in the outer Kuiper Belt. But once you get out to the very limits of the Oort cloud, you're really at the very limits of the sun's gravitational influence in its local environment. That these objects, these icy objects, are just one bad day away from drifting out of the sun's influence and being caught by some other star. And you know, that's how you get interstellar objects. So they just interact just gently with each other and go into a more spherical form around the solar system. Your crazy uncle, how to travel at light speed times 10. We don't know of any practical way to go faster than the speed of light. And it's funny, like there's this thought experiment that I really enjoy, which is that if traveling faster than the speed of light was possible, then we would see civilizations that were really far away would be able to make the journey to get to us. Like not just the ones that are stuck having to go slower than the speed of light, but you'd have ones that could go 10 times, 100 times, a million times the speed of light. So the entire, more than the observable universe would be able to access our part of the universe. And so we should see lots more aliens, and yet we don't. So right now it appears that going faster than the speed of light is impossible, that it violates the laws of physics as we understand them. Now, obviously, we might not understand the laws of physics correctly, that in fact, there are things that would allow for you to travel faster than the speed of light. But the fact that we don't, sort of like the light speed paradox, we don't see people going faster than the speed of light. Therefore, it appears that the laws of physics as we understand them are correct. It would be amazing. And like, this is what science fiction does to our brains. The science fiction says, boy, it'd be a much better story if you could travel faster than the speed of light. So we're just going to say you can travel faster than the speed of light. Done. Boom, right? What is how do you travel faster than the speed of light? Unobtainium, warp drive, the Stargate, the hyperdrive, jump gates, whatever science fiction terminology you want to use, sublight to allow you, or subspace to allow you to move faster than the speed of light. Mycelial network, I don't know. But like, it sucks. Like, we want that bold science fiction future to be like what the stories have told us. And yet nature does not want to play ball with us. She doesn't want to, give us the science fiction future we richly deserve. Louis Carnero, Fraser, what are your thoughts on the theory of traveling through wormholes? Will it be possible one day or just science fiction? So this is sort of related to the warp drive thing, which is, theoretically, mathematically, that you could have some bridge, like you have wormholes, you could have some kind of bridge between them, and you could theoretically travel through them. But this is just like mathematically theoretical. And one of the sort of requirements of the wormhole, if it is even theoretically possible, is that the moment any energy or mass goes into the wormhole, the thing collapses. So even if these things could possibly exist, there's no way to send anything through them. But again, we're back to the paradox. The fact that we don't see people traveling through wormholes means that there probably aren't wormholes, and that we probably can't travel through them. It's just like another way to give us some kind of science fiction future. And like, don't get me wrong, I love me some Stargate. Stargate is the best science fiction show ever made. And yet, the wormholes that make it such a civilized way to travel from star system to star system probably will never be a thing that we can walk through. But there is a lot of active research, way more active research on wormholes than there is on, say, warp drives, because at least the math seems to be there. And so there are regularly papers, people talking about how, some really cool ideas. Like if there were wormholes, then you would, if things lined up perfectly, you could see stars or galaxies on the other side of a wormhole. So it would be like this moment, sort of imagine you've got a hole in your roof and lights going up past your roof. And every now and then a light lines up perfectly and you suddenly see this light in your roof. I don't know, that's a bad analogy. I apologize. First time I've ever tried it. And so you could be looking at the sky. You could do this survey of the entire sky. And then you're just waiting for this moment where things suddenly appear out of nowhere and then disappear again. And not in a way like a supernova is going off. Like suddenly there was a star and now the star is gone. And that could have been that you were looking through a wormhole, a natural wormhole that was out there. And then of course the other idea is that wormholes can collapse, and maybe they give off a burst of energy when they collapse. And so people have proposed ways that we could watch the sky looking for the collapse of wormholes. So while warp drives are just nobody even knows where to start on warp drives. Wormholes at least have a mathematical structure that is theorized, and so we could look for them to be naturally forming. But nobody can think of a way practically that you could create a wormhole and travel through it and so on. Arjun, could we detect the Oort clouds or Kuiper belts of exosystems? So astronomers have detected the Kuiper belts of exoplanetary systems, that if they're ridiculous, like they are solar systems that are extreme compared to the solar system, that maybe there was some kind of large icy object that was shattered recently, and so they've been able to see this giant ring of icy material around some other star system, and but not an Oort cloud. That has never been seen. I mean, we haven't seen our own Oort cloud yet, but people have seen the equivalents of Kuiper belts around other star systems. Some water. Ian A. James, it's hard to reconcile national security laws when it comes to the subjects about advanced propulsion. I wonder why we don't address this more directly. So there's sort of like two camps that think about this kind of thing, right? There is scientists and physicists and people who understand the math involved and the scale of traveling from star system to star system, the complexity of what it would take to have a spacecraft that had any kind of advanced propulsion system. And then those who, let me take another crack at this. Okay, let me just again. Ian A. James, hard to reconcile national security laws when it comes to these subjects about advanced propulsion. I wonder why you don't address this more directly. The thing with advanced propulsion systems is that they're going to require incredible levels of energy. When you think about the possibilities, you've got fusion drives. Even those don't really get you to good interstellar velocities. You really need laser sails and antimatter. And so like with a laser sail, you're having to build a laser that is orders of magnitude more powerful than the most powerful lasers that are being used on Earth. And the most powerful lasers on Earth are getting kind of dangerous. They have lasers that can at range do damage to the optics of vehicles, can, burn holes in metal at certain distances. I mean, lasers are getting more and more powerful every year. And you could put one of these super powerful lasers in space. Yeah, it could accelerate a spacecraft to relativistic velocities, but it could also be used to blast holes in your enemy's satellites. So there are going to be definitely sort of dual use national security concerns with operating very powerful lasers either on the surface of the Earth or putting them in space where they can direct their beams down on planet Earth, but could also accelerate a spacecraft to travel to Alpha Centauri. That'd be cool. And then antimatter is even scarier, right? Antimatter, that any amount of antimatter, you put it with matter and they will annihilate with this pure E equals MC squared explosion, and they will generate pure gamma radiation. And so tiny amounts, grams of antimatter is the equivalent of bombs. It doesn't take much to be able to mimic the power of a thermonuclear weapon with a tiny amount of antimatter. So the challenge of getting antimatter is you have to make it. You have to dump in enormous amounts of energy to create the antimatter in the first place. And then you need some way to store it. And so if people are capable of producing antimatter, then you have got a gigantic challenge on your hand, because they are able to generate gigawatts of energy, store antimatter. Like, that's all kind of scary. So it's an interesting kind of dichotomy that the kind of technology that would be required for us to be able to reach out to go to another star system is also dual use some of the most scary, terrifying weapons that humanity could possibly imagine. You know, if you could build enough energy to send your spacecraft to Alpha Centauri and like store up that amount of antimatter, you've got a mega bomb if you needed it. And so I think moving forward, we're going to have to figure out ways to be able to do that. And so people have proposed that, you know, if you're going to build the laser, you put the laser on the far side of the moon, or you put the laser on the far side of the sun. So it's just like, it can't cause any harm. And then if you're going to build antimatter, like maybe you build a giant particle accelerator and you put it out at the orbit of Jupiter, and that's where it builds its antimatter, so it can't potentially be used as a weapon against Earth. But yeah, like just in general, as humanity is capable of building more and more powerful things, harnessing more energy, harnessing more intelligence, these things can be dangerous to us. You know, the nuclear weapons versus nuclear energy is sort of the perfect example of this. And we are just the beginning, you know, really, of this long curve of humanity's growth in technology and capability. The scariest is yet to come. SM colons. Any progress on disappearing stars, like the 3 that disappeared in one telescope view in less than 30 minutes? So there was, I'm trying to remember the specific story. So there was like someone was looking through archival photographic plates from like 100 years ago, and they saw stars disappear from those plates. And I know that, and like, it's sort of getting mushed in my brain at people seeing objects moving through archival plates as well. So I haven't heard, like, there hasn't been a lot of science or a lot of people doing surveys on this. You know, and people are proposing that maybe there were some kind of satellites before the satellite age. But the other kind of direction that this story is going on is this idea of unnova, of stars that go supernova, or at least they turn into black holes directly, that they never actually detonate as a supernova. They just implode and disappear, which is kind of scary, right? You could have a star with 20 times the mass of the sun, and it's reaching the end of its life. It's ready to detonate as a supernova, and then it just goes... it's gone. And that astronomers are seeing more and more examples of these direct collapse unnovas, that instead of them going supernova, the star just is gone because it just imploded itself into a black hole. Terrifying. And I really want that to be true. Like, I want that to be one of the ways that stars die. And then we'll figure out, like, what is the mechanism, what causes, what makes those stars do that. But it is just like, just imagine watching it happen. There's a star, and then the star just sort of and it's gone. Leaf Binder. If moon tickets were only $500, would you go see it? Absolutely. Yeah. If I could take a flight to the moon for $500, done. Sign me up. You know, if I could take a flight into low Earth orbit for $500, I would probably, like, if it was safe, like airplane safe, fly me to the moon, $500, sold, I'm on board. But it's not. It's hundreds of millions of dollars right now. So unfortunately, it's too expensive. But if you offered me a $500 ticket to go to Mars, I probably would turn you down, because a trip to Mars is 3 years, high radiation environment, incredibly dangerous. I would love to teleport, to take the Stargate to Mars and stand out on the surface of Mars in my spacesuit and go, whoa, I'm on Mars. How crazy. This is cool. And then teleport home. And going to the moon is roughly that. Like, yeah, you got to take a couple of days to get to the moon. You stand on the surface of the moon. You're like, I'm on the moon. And then you come home. But to go to Mars or other places is just such a long journey. I don't think I would want to do it. I'm happy that other people want to do it, and I will cheer them on, but I'm not that guy. Dougal, have you ever recognized one of your Patreon supporters during your one-on-one discussions? Like, are you asking, like, is there a celebrity who is one of my patrons and I do the one-on-one discussion? I'm like, what? You're my patron? Yes. Yes. It has happened several times where, one, I saw the name and I was like, nah, it couldn't be. And then I met them and I'm like, yep, it was them. And then two other times they were sort of incredibly influential people in fields that I really admire. And it was an absolute pleasure to talk to them about their lives and their work and their job. And I'm sorry I can't provide any information. I need to provide, confidentiality, patron creator privilege. But yeah, there's been these times where I cannot believe that this person is my patron. The one-on-one interviews are so much fun. If you haven't done this yet, if you're a patron, and you haven't signed up to do the interview with me, why not? It is literally me talking to you, just like this, except you talk to me and I talk back to you, and it's about 15 minutes, and we're just hanging out and chatting about. Well, I have a bunch of questions for you, but then I will answer any questions that you've got about space and astronomy. And I've mentioned this many times. Like, I cannot believe more creators don't do this. It is super fun. I guess if you enjoy talking to human beings, which I do, right? Like I'm a total extrovert. I really enjoy meeting new people. It is like only one time has it gone sort of in a weird direction where the person essentially signed up as a patron to be able to pitch their alternative theories about the universe at me. And I'm like, okay, great. Thanks for your money. But I'm not going to report on your theory. But the rest of the time it's super good. So it's just like, I love talking to new people. And I hope you see that in the interviews that I do. And then as creators, when you make stuff on the internet, your experience is just negative, that people shit on you, right? Like, it's hard, it's brutal. And so to just like talk directly with the people who actually enjoy your work so much to the point that they want to support you every month is a genuinely positive experience. It lifts the spirits, replenishes the "why am I even doing this?" part of your soul. And then it gives me real, actual, practical advice. If I'm making some mistake or if there's something that I'm doing that I could do better, I'll find out right away. And then I discover all of the really cool stuff. So all of the TV shows, movies, I ask them, like, just what media, what books should I be reading? What games should I be playing? What are some other YouTube creators I should be following? And so I've a lot of the favorite stuff that I watch now is because, if a person has good taste to watch us, then they will have good taste on the other media that they watch. And I find out about tons of stuff through that. So, it's so much like and I totally get that it feels very scary that it is this, especially for women, right? Like, I can't imagine how much potentially scary it is for women who are going to be having a personal conversation with a fan, right? Because it could go in weird directions. But I think just like in general, if you can set up the right kinds of fail-safes or whatever, it's a really meaningful experience that you are directly connecting. And it feels like this is going to sound super weird, but one of my great sadnesses as a creator is that I don't get to meet you all. That when I go to conventions and I get a chance to hang out with with the people who watch our stuff, it is like 99% of the time, not just enjoyable, but like you're my friends. Like you would be my friend. Like if we lived in the same city and we hung out, there would be, we would have a ton in common and we would chat, and the conversations are very entertaining. And I always feel kind of just like sad, like just in general, about all of the people around the world that I will never meet, that I will never get to know, that I'll never be able to be friends with, because friendships are so meaningful. And that I have a ton of good friends and I spend time with them in real life. But I feel this sort of grief for the friends that I will never make, which I know kind of sounds really weird. And that this gives me a way to kind of salve that grief a little bit by having these sort of temporary conversations, these short-term conversations with lots of people. And I'm up to, how many of these have I done? Interviews 1,261. So I've had a 15-minute one-on-one conversation with 1,261 people. So I'm serious. Like I'm not messing around here. I am still continuing to do this, several interviews every week. It's a good time. Zeppin, Stargate actor? No Stargate actors. Neil deGrasse Tyson? No Neil deGrasse Tyson. That would be cool. I mean, I've talked with Neil deGrasse Tyson in the past. We hung out at the American Astronomical Society meeting, and I gave them some advice when they were setting up their live stream video like 10 years ago. So that was cool. Luke Skywalker, are your real life friends into astronomy as well? I mean, everybody's into astronomy, right? So like my wife loves astronomy and my kids love astronomy, and my friends, if I said, hey, let's go watch the meteor shower, they're like, yeah, I'm into it. And they'll often send me stories. My wife is often sending me stories of stuff she's seeing in astronomy news. And sometimes it's totally new to me, or I give her more context, then she's sort of regrets sending me information about astronomy. My dad is into astronomy. Everybody loves astronomy. So yeah, my friends and family are all subsets of human beings, and all human beings love astronomy. I've never met, have you ever met a person where you're like, hey, there's a meteor shower tonight, you want to watch? And like, nah, that's dumb. I hate space. People watch science fiction movies. They like Star Wars, Star Trek. They love TV shows. We're all fascinated by space. So, yeah. So it's a very, it's as opposed to me having like a really obscure career or hobby. Like, are your friends into basket weaving too? Not really. Nobody wants to talk to me about basket weaving. I just basket weave alone. Nick D730 just got here. Aren't there mass concentrations that make low orbits unstable? Yes. Go back to the beginning of the episode. I answered that one. Where are we at? 6:30. Apologize, just looking at the current questions. CeeLo 87, have we ever witnessed an object from our solar system get flung out at escape velocity, not including our own craft? No. So the thing that we would be looking for would be a long period comet, something that is right at the very limits of escaping the solar system's influence. Like it just takes a kilometer per hour, per second difference in velocity to turn it from something that's going to go way back out into the Oort cloud to something that is going to leave the solar system entirely. And so it has absolutely happened, because all you really need is a three-body interaction. So, you have this long period comet, it falls into the inner solar system, it gets relatively close to the Earth and the Moon, gets tweaked by the gravity of the Earth and the Moon, gets tweaked by the gravity of the Sun, and now it is on an escape trajectory out of the solar system. And the fact that we see interstellar objects tells you that this process is happening all the time. But I can't think of any examples where a comet came in, we could calculate that it got its orbit tweaked enough that it was going to then go on to an escape trajectory out of the solar system. The only thing that we have sent, as you asked, is our own spacecraft. Like we've sent the Pioneers, the Voyagers, and New Horizons on an interstellar trajectory. JJ's Quest. Doesn't quantum entanglement imply information travels faster than the speed of light? No. Quantum entanglement, sort of spooky action at a distance, is sort of like one of the outcomes of quantum mechanics, but it doesn't allow you to communicate any information faster than the speed of light. And so it doesn't violate the speed of light. Mad Million, if you're on your way to Mars, you can only eat one cuisine. What would you go with? I mean, like probably Mexican, Tex-Mex, right? Is the best food in the world, right? Isn't it? My wife is American, and she was living in Texas, and I was coming to visit her, and I'd come visit her for a week, and I was like, just to warn you, we're going to go eat Tex-Mex for breakfast and dinner, and like lunch probably too, every day. She's like, yeah, no, I'm in. I'm all for it. So, and we did it. So, man, eating Mexican food in Texas or California or Mexico, but Mex-Mex is good food as well. But like Tex-Mex with like cheese, it's so good. So yeah, I would probably do Tex-Mex, would be the cuisine that I would want to eat. Blackberry, Blackberry, looking like near-Earth object 2024 YR4 isn't predicted to hit the moon in 2032 anymore, but at any rate are moderately sized objects hitting the moon a threat to Earth from impact ejecta. So when 2024 YR4 was first discovered, astronomers had like a non-zero chance that it was going to hit the Earth in 2032. And then they ruled out that it was going to hit the Earth, but there was still a non-zero chance that it was going to hit the moon in 2032. And now they've ruled that out as well. So it's going to get very close to the Earth and the moon, but it's definitely going to miss us. But if it did hit the moon, it would be big enough that it would carve out a bunch of debris. The debris would make its way down to the Earth, would endanger our satellites, but would also cause the mother of all meteor showers. And so that process does happen. Plenty of telescopes watching the moon see objects strike the surface of the moon and cause little flashes in the moon. But we have never seen anything that is so big that it has actually churned up debris that has then made its way down to the Earth. But when you look at the craters on the moon, it has happened. And probably in human history, there's probably a time when humans were around and something relatively big crashed into the moon, like maybe something that was, 500 meters across, and then that dug up a bunch of debris, and the debris made its way down to the Earth, and then they got this incredible meteor shower that lasted for quite a while. That would be amazing, apart from all of our satellites being at risk. But would I pay the price? I guess it wouldn't be my price to pay. But if I could press the button and no one knew that I was creating the mother of all meteor showers with a risk to satellite infrastructure, would I press that button? I don't know. You're going to have to decide for yourself. Mist Solar. What evidence would confirm panspermia as a consensus? Well, I mean, so theoretically, like the case for panspermia is that theoretically objects can crash into the surface of, say, Mars and hurl debris into space. The debris, microbes on board the asteroid debris can survive in space in hibernation until the asteroid lands on the Earth. It re-enters or enters the atmosphere of the Earth. They can survive that. It crashes onto the surface of the Earth. They can survive that. And then they can pop out of their hibernation and go about colonizing planet Earth. And this has been considered a real possibility for how life formed on Earth, is that maybe it didn't form on Earth. Maybe it formed on Mars. And then life was able to just travel from Mars to Earth. And that if we find life on Europa, find life on Enceladus, maybe that life will be related to us because of this idea of panspermia. So every piece of the chain has been essentially verified, that we know that there are large objects crashing into planets and moons out there in the solar system and causing material to go into escape trajectories. Like, that has been seen, or that has been calculated. We see asteroids that were caused by some smash into a planet. We know that there are hardy life forms that can withstand being in deep space for long periods of time, for hundreds of thousands, potentially even millions of years, depending on how deep they are inside the rock and what the conditions are. We know that things can withstand the heat and the temperature and the pressure of entry into the atmosphere of Earth. And so all of the bits of the chain have been effectively confirmed, but the life has not actually been found. And so the thing that it would take to confirm panspermia is that we would actually have to find life on Europa or Enceladus or on Mars, and then prove that there is a common ancestor between that life on those planets and us. And that's relatively straightforward, right? That once we get our hands on life from another star, from another place in the solar system, if it is related to us, then the methods, the techniques of analyzing the DNA will work. And yet if it is totally unlike us, if it is nothing in relation to us, then those techniques will not work. And so that they will, we'll find out. And so then if we do find this life, then we just have to trace the common ancestor. And this is you can take the DNA from me and the DNA from my hated enemy, the mushroom, and you can find out when me and mushrooms shared a common ancestor. You can determine when avocados and I shared a common ancestor, and you can determine when archaea and I shared a common ancestor, and you could determine when life on Earth and life on Mars shared a common ancestor. And then that would give you a sense of when the panspermia event happened. Did life go from Earth to Mars, or did life go from Mars to Earth? You could determine all those things, but you have to get the life. So that is the thing that would be required. Emilio Waneri, what was your favorite programming language? So we learned, I don't know if you call HTML, CSS, a programming language, JavaScript, Java, C, C#, a little bit of C++, Perl, PHP, Python. So Python is the software that I use today, but I really liked PHP. I would say, if I had to sort of like the programming language that I found allowed me to do the kinds of things that I wanted to do, PHP was great, because I had really nice integration between HTML, because everything I wanted to do, I wanted to be expressed in web pages. I'm a huge fan of just the web as a way of interacting with code, web servers. And then JavaScript on top of it to provide more intelligence to the things that you're putting into your website. But the PHP was the language that I found. I find Python is very powerful and it's very well used and it has a lot of great stuff. But it just has never felt as natural to me as using PHP. So that was, but like, that's just like I'm a product of my era. Oh, and I learned Fortran and Pascal and BASIC. Yeah. I never bothered with assembly language, but I never became a great programmer. I pretty quickly moved to managing programmers. I was more of a product manager than I was a developer. Someone asked anything new on the shelf. So I picked up two things I was going to add to the shelf. So I picked up, when I was in Japan, I picked up a Godzilla toy, and I regret only getting one because I came home and I was like, I got to give this to my kid. So I gave the Godzilla, like a little Godzilla action figure, to my younger kid. And then I was like, okay, I'm in Japan. I'm totally going to get into this gunpla hobby. And that is like snap tight mecha robots. So you have this, it's like a model building of a robot, but you don't need any glue. Everything snaps together, and you buy these really nice clippers that clip the plastic on the model, and then you can clip all the bits together. And I gave that to my eldest. So I was going to have a mecha model behind me, and I was going to have a Godzilla statue behind me, and then I gave both of them away. And I'm like, I totally screwed this up. So next time I go to Japan, and that's going to happen fairly soon, I'm going to bring home more stuff. I totally, like, there's so much cool food and flavors of soy sauce and robots that you can snap together. It's a wonderland. It's a nerd wonderland. And I really should have brought more back and put a bunch of stuff behind me on the shelf to sort of commemorate the recent trip to Japan. PHP Echo, thanks. Yeah. Sorry, just looking. Dougal, Japan is now your favorite vacation spot? Oh yeah, so far by far. Japan is amazing. Like I've still scratched the surface, but now I've been there twice, and my wife loved it. We came back from Japan, and I was like worried that, like, I mentioned this last week or 2 weeks ago. She like doesn't like human beings, and yet loved Japan. And she was like, I loved every minute of this. So that was so great, because I love every minute of being in Japan. And so it was so great for my wife to love every minute of being in Japan as well. And it was sort of like, I felt it was sort of, it could have gone horribly wrong. She's packed in like sardines into a metro system in Tokyo. And then she was like, get me out of this place. But nope, she really enjoyed it. So yeah, Japan is now high on the list of vacation spots, and so far we've just done the big places. So I really want to go back and do small towns, small places off the beaten track, like really get more of an experience of off the main track Japan. But yeah, like I've done a lot of traveling at this point, and Japan is one of those places where I'm like, I could live here. I could totally live here. Yeah. Arjun, do you ever plan on visiting JAXA? Do they allow that? Yeah. So you can go to the Japanese Space Agency. It's outside of Japan, outside of Tokyo. It's like an hour and a half train ride out to JAXA, and they have the tours are in Japanese, and apparently they don't even have an English version of the tour. So You got to be able to speak Japanese to be able to take the tour, but they do have museum exhibits and you can kind of wander around and check out the facilities. And then they have the launch complex is this island called Tanagashima Island. Tamagashima. Anyway, it's this island off the south of Japan, and that's where they launch all of the H3 rockets from. And it's this kind of cool little surf spot island that also they launch rockets. And I would love to get down there and watch a rocket launch at some point. Darth X, your wife doesn't like human beings. Good catch, man. Yeah. She is, loves animals, hates human beings. So I'm really lucky, she loves me. Whoa. Paige Potter, any thoughts of Neil deGrasse Tyson's Take Me to Your Leader? I haven't seen this. Was this like a video that he did? Oh, this is his new book. Oh, I haven't read it yet. Came out fairly recently. Okay, I'll check it out. Church discography. Why can't they just create a magnetic field around spaceships to protect passengers going to the moon and beyond? Are you trolling me? Is that what this is? You're trolling me? Why don't they just put windshield wipers on the Mars spacecraft to get the dust off of their solar panels? Why don't they just? Yeah, people have been trying to come up with an idea for this since the 1960s. No one's been able to figure it out so far. Paul Michael Friedman. Yeah. Let's see. Michael McConnell, other than a solar filter, what accessories should I be looking at as a new first-time 6-inch Dobsonian owner? Congratulations on joining the elite club of the non-elite club of owning a Dobsonian telescope. That's amazing. That's so great. I finally someone's listening to me. People who ask like, what is the first scope that you should buy? Get a Dobsonian. And a 6-inch Dobsonian is great. Like it's a lot of telescope. When you think about the size of the, I have this really fancy apochromatic refractor. It's a 70 millimeter. 6 inches is way bigger than that. What is it, 130 millimeters? So a much bigger telescope. And that's just like a 6-inch telescope. And you can make Dobsonians on your own. So like, I'm just excited about that. So what are the good accessories? So like good eyepieces are the thing you want to invest in. And when you buy your sort of baseline Dobsonian telescope, actually I should have an eyepiece. Do I have the eyepieces here? Yeah. Don't break it. Okay, good. Yeah, this is great. I can give you some actual examples. So when you buy a new telescope, I don't even have it here. Yeah, all right. The eyepieces are going to be small. So they're going to be, this isn't even a great example of it. But they're going to be little, right? This is actually a different tool, but the eyepieces are going to be very small. They're going to be like 4 millimeter. They're going to be 10 millimeter eyepieces, and the quality of the glass is going to be fairly low. And so the thing that I recommend is you get like a really nice wide field eyepiece. So this is a 38 millimeter eyepiece. And there's sort of fancy versions of this. There's a company called Plossl that makes really good eyepieces. And then there's and so like, look at the size of this, right? Like this is a lot of eyepiece. And so it is a very, very wide field of view in the sky. And that's great for looking at Andromeda, or for like open star clusters, or if you just want to look at the Milky Way. And it's so much glass that you're just falling into the sky. And so the eyepiece is going to make a huge difference. And, you know, a lot of times we're trying to get these really high magnification eyepieces, where you've got something that's like a 4mm eyepiece is going to let you see Saturn. You're going to be able to see the rings of Saturn. And that's great. Like if you want to see the rings of Saturn, you're going to need that really small apertures, like 4mm eyepiece. But you know, the view is going to be shaking, and you're going to have to dial it in perfectly to be able to see it. But a lot of the things in space just look really great when you're seeing them at a larger scale. You know, you still want to have a magnified view of it, but you don't want it to be just staring through a straw. And so these bigger eyepieces. And so see if you can get your hands, you know, depending on what the mount is on your telescope. My 8-inch Dobsonian can fit a 2-inch eyepiece. And so I use this really big one, and it's just beautiful. So I would invest in some better eyepieces is a place to go. And then you can take them from telescope to telescope. You know, you may, if you sell the 6-inch Dobsonian, you get the 8-inch Dobsonian, you've still got your eyepieces that you can use along the way. The solar filter is great. And, you know, you got to be really careful, because you need to make sure you got like high quality solar filter that covers the end of the telescope. And then you can look at the sun, which is great, because the sun is like a really wonderful target. It's big, right? It's as big as the moon in the sky. And if you've looked at the moon with your telescope, the moon looks great. And the sun looks great too. You can see the sunspots, and then under different kinds of filters, you can see different stuff that's happening on the sun. And then I would generally invest in a better finder scope. So there's a Telerad. I have one actually here. It's there. It's there. Okay. Yeah. So actually, I've got a Telerad that I haven't installed it on my 8-inch. Right. So you can get. It's kind of. You can look into the sky, and you can line up objects that you're looking at with your finder. And so it just lets you find stuff faster with sort of perfect alignment. So you can, you know, generally the finder scope that comes with a Dobsonian is, you know, it's mediocre. Right? All the parts in the telescope are sort of, you know, mediocre, except for the actual scope itself. And so you can get a new finder scope for it. And then, man, you can get an eyepiece adapter, so you can clip your phone to your telescope. And taking pictures through your telescope manually, like holding your phone up, is a total pain. And so these mounts are great and allow you to take really cool pictures through the telescope. And so that's always good as well. So yeah. Get a better finder scope, get better eyepieces, and get a mount that allows you to take pictures with your phone into your telescope. And again, congratulations. What time is it? Ooh, we're almost at the end. Nick D. Robert Zubrin downplays the risk of Mars biocontamination due to the natural transfer of material between Earth and Mars. Do you agree with him? So this is where I have to sort of say, like, I'm not a scientist. And so his case is compelling, that if panspermia is true, then Earth and Mars, Earth and Europa, Earth and Enceladus, you know, all these places are transferring material all of the time. And that that Mars is, you know, whenever you have these environments, the one that is harsher is often more easily colonized by like when you think about a place like Australia, that Australia has just been totally colonized by prickly pear cactus, that it had no natural defenses against it. You know, you go to the Galapagos Islands, and the frigate birds will let you, the boobies? Anyway, you just come up and grab their eggs. They're just, they have no natural defenses against anything. So So the risks are probably very low that life forms that have been evolving in separate environments for billions of years probably cannot infect each other. But why take the risk? That this is the kind of thing that you could mitigate, that you could go, well, let's, the chances are extremely low. And we've retrieved samples from asteroids now and brought them back down to Earth and kept in sterile environments and kept them away. But, there's only so far you can go, and eventually maybe something will leak out. So why take the risk? That's all. And so there are ways that you can mitigate the back contamination from Mars, and you can mitigate the forward contamination to Mars. And I think, the Zubrin is an accelerationist for the human exploration and human colonization of Mars. He is like, let's go, 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 and damn the consequences. And so one of the consequences is the contamination of Mars from Earth life. And we don't know. Like, it could very well be that there is just no place there's liquid water, and that no amount of Earth life would ever find its way down to that liquid water, and therefore the risks are effectively zero. But we don't know. So we should not take unnecessary risks. And people have come up with perfectly viable strategies for containing an area, studying places very carefully, removing as many contaminants as possible, and just being very, very careful about the way that you explore Mars to minimize the chance. Because it would just totally suck if we infect Mars with Earth life before we can study it and learn anything about it. Like, everywhere we go, we dig underground and we find cyanobacteria again. That would suck. So it's just one of those things that we should, it's a thing that we can control. It's a thing we can be careful. And if it slows down the exploration or the colonization of Mars, so be it. We have learned, this is a lesson we have learned we have failed to learn so many times here on Earth, that invasive species can cause devastation to a natural environment, and that we think we know the variables. We think by releasing this fish and that mongoose and this moth and that beetle that we're going to make nature all balanced again. And it turns out we didn't understand it as well as we thought we did. And then there are consequences. The consequences run roughshod, and then we spend millions and billions of dollars cleaning up the mess, if it's even possible. So I totally get that Zubrin wants us on Mars yesterday. But, until someone can present a compelling case for what is the business model for colonizing Mars, it's right now, and will be for the foreseeable future, a scientific question. What, it is in the realm, the domain of exploration. And if we're going to explore, let's be careful. Okay, we've reached the end of this episode.